Today we have the pleasure of having Shreya, who's now from Stanford, and she's going to tell us about quantum chaotic systems and black holes.
Okay, great. Thanks a lot for the invitation. It's a pleasure to be here. So I'm going to be talking about some work in progress with two great collaborators, Haifeng Tang, who is a PhD student at Stanford, and Jinsao Wang, who is a postdoc at Stanford. Okay, so let me start with some background and motivations. Let me first start with some motivation from general chaotic quantum many-body systems. Okay, so in such a system, suppose we start with some initial pure state psi 0, and then we evolve the system. So at later times, we have the time evolved state psi of t, which is evolved by some Hamiltonian. Then from the fact that the system is chaotic, quite generally, we expect that this late time state macroscopically resembles an equilibrium density matrix, such as e to the minus beta h. And we have the sense that the state reaches some kind of steady state at late time. So in particular, this is captured by the fact that e to the minus beta h does not evolve with time at all. It just commutes with the Hamiltonian. But if we actually look at what this state psi of t is, then from the fact that it's obtained from this kind of unitary evolution, we can see that it's decomposed in the eigenbasis of this kind of sum of phases multiplied by some states, and this necessarily has to continue to evolve with time at any time. Okay, so there seems to be some kind of tension between our intuition from thermalization and just what we know about unitary time evolution. And we can make this tension more precise in this talk by considering an operational task of estimating time. And I'll explain what that means. By using this sort of precise characterization of time estimation, we'll see under what constraints our intuition about reaching some steady state is approximately correct, and in what sense, if you don't impose any constraints, then the intuition is completely wrong. Okay. So another motivation for looking at this question is in the context of black hole physics, where we consider some star, which we can initially take to be in some isolated pure state psi 0. And we know from Hawking that the star collapses to form a black hole, and eventually the black hole emits some thermal radiation. Okay, so at late times, degrees of freedom, like in this cartoon, are getting transferred from the black hole into the radiation. And in many ways, this combined state of the black hole and radiation at late times resembles some kind of thermal density matrix. Okay, but there is a lot of evidence that black holes are governed by a unitary chaotic evolution. And so, in particular, this means that the combined state of B and R at late times must be some kind of thermalized pure state, similar to the kind of state that I wrote on the previous slide. And so it, again, cannot strictly stop evolving with time. Okay, but in this context, a natural question to ask is, suppose you have access only to the state on the radiation for some particular sizes of the black hole and radiation, then by looking at this state, does it appear that the system is not evolving with time? Okay, and this is a question that we'll address in this talk. Right, so our main goal in this talk is to sharpen the distinction that this e to the minus beta h does not evolve with time, while psi of t necessarily evolves with time. But often in the context of the black hole information problem, we're used to discussing a different distinction between these two states, which is that this thermal density matrix contains very little information, whereas the time evolved state psi of t contains information, but in some very scrambled form. Okay, so let me spend a couple of minutes reviewing sort of how we quantify these statements about containing or not containing information and what methods we use to analyze this question. Okay, so one way to quantify whether the state contains information or not is to consider some subsystem and to consider its entanglement entropy, which is defined in this way in terms of the reduced density matrix of the subsystem. Okay, and we can consider various different relative sizes of the A system and its complement, A bar. And if we consider the thermal density matrix, then we find that this entanglement entropy is just proportional to the volume of the subsystem for any subsystem. So in particular, if we consider the whole system, then the entanglement entropy or von Neumann entropy is proportional to the volume of the whole system. So it's very large, and having a large entropy roughly means that we have very little information. Okay. But if we consider a thermalized pure state, like the state obtained at late times from some chaotic time evolution, then we find that the entanglement entropy is proportional to the minimum of the volume of A and the volume of A bar. Okay, so up to half of the system, this just agrees with the answer in the thermal case, but then for more than half of the system, it's a smaller answer. And in particular, if you consider the whole system, then the value is just 0 from this formula. Okay. Good. And this formula that the entanglement entropy of a subsystem is proportional to the minimum volume of A and volume of A bar has been very important in our understanding of both general chaotic systems and black holes. And this was first understood by considering a model for the late time psi of t using just random pure states. So we have imagine having some finite dimensional Hilbert space of A and A bar, and then we consider completely random states, random pure states on this combined system with a uniform measure. And we find a formula of this kind for the answer. And this was first considered by Page. And if we assume that the combined state of the black hole and radiation during the evaporation process is of this form, and we take the subsystem A to be either the black hole or the radiation, then in that context, this formula implies the Page curve for the evolution of entanglement entropy of either the black hole or the radiation. Okay, so this blue curve is what you would naively think from a semi-classical gravity calculation is the dimension of the black hole. The red curve would be the dimension of the radiation from Hawkins analysis. And what we find from this formula is that we should expect the entanglement entropy of either the black hole or radiation to follow the minimum of these two curves, which is the solid line. Okay, so based on this, the entanglement entropy of the radiation stops agreeing with that of the thermal state after the Page time, when the size of the radiation becomes bigger than that of the black hole. And from the fact that it no longer agrees with the value in the thermal state, we expect that the radiation in some sense contains information after the Page time. Okay. But this is still a little bit vague using entropy to quantify information, but we can make this much more precise by considering an operational task. Okay, so this was done by Hayden and Preskill many years ago now, where they consider the following question. So suppose that we prepare a small system, which we can say is someone's diary, in some quantum state rho d, and then we throw it into the black hole. Okay, and then once we throw it into the black hole, the whole system evolves under some unitary chaotic evolution. And then at a later time, the black hole has become smaller and it's emitted some radiation out. Okay, and now the question we can ask is, can we do anything on the state of the radiation, this rho r time t, in order to recover the original state rho d of the diary? Okay, so this is a very precise, operational question, and in a very precise way, if the state rho r of t contained no information, then this recovery has to be impossible. Okay. And what Hayden and Preskill found is that the recovery is indeed very poor before the Page time, when the dimension of the black hole is of the radiation is smaller than that of the black hole. But the recovery becomes almost perfect after the Page time. Okay, so there is a precise sense in which the radiation contains no information before the Page time and contains the information of any small subsystem like this after the Page time. Okay. Any questions about this? Okay. So in this talk, we'll introduce a new operational task, which will be related to the question I mentioned earlier about time evolution. Okay, and our new task is to try to use the radiation as some kind of clock. Okay, so what I mean by this is that we are given the state of the radiation at some time t plus delta t, which is close to some known time t, but we don't know exactly what delta t is. And what we want to do is somehow make measurements on R and try to use those measurements to figure out what delta t is. Okay, so in this case, if this reduced density matrix of the radiation was not evolving at all with time, then this task would have to be impossible even in principle, because nothing about the state is changing from one time to another. So of course you can't do anything to estimate delta t. And similar to Hayden and Preskill, we'll find that this time estimate will be very unreliable before the Page time, but it will suddenly improve after the Page time. Okay, and like in the approach of Page and Hayden and Preskill, we'll come to this conclusion by studying universal properties of unitary chaotic quantum time evolutions. Okay. Okay, so to make this question about parameter estimation, about estimating time more precise, I need to introduce a little bit of background from the field of quantum metrology. And this relates to just general estimation of any parameter using a quantum state. Okay, so now let's just consider a completely general setting where we have some family of quantum states which are labeled by some continuous parameter x, which we'll eventually take to be time in our case. And suppose that we're experimentalists and we're given n copies of the state rho at some particular value of x. Okay, and now we want to figure out what x0 is by making measurements on the state rho of x0. Okay, so for example, suppose that we have some spin 1/2 chain and we choose to measure the system in the Pauli Z basis on all sides, which is probably the simplest basis to measure in. So we have the first copy, we measure the values of Z1 through ZL, where L is the system size, and we get some string of measurement outcomes. Then we repeat this process for each copy and we get some set of strings, psi1 through psi n. Okay. And now, based on these measurement outcomes, we want to come up with some kind of estimator function, which I'll call xest, which tries to guess what x0 is. Okay. So our question will be, how well can the best possible function xest do at estimating the value of x0? And if no estimator is able to do a good job, then this indicates that the state is not changing very much with this parameter, at least with respect to the measurement basis that we're looking at. Okay. So to quantify the accuracy of the estimator, we can use some kind of variance like this, where we average. So for any given realization of psi1 through psi n, this quantity measures sort of how far our estimate is from the actual value of x0. And then given the probability distribution associated with the size in our state, we can consider the variance of this object. Okay. And now this has become just a question about classical probability distributions, right? So we have some parameter x0 and some classical probability distribution, and we're given samples from this probability distribution, and we want to figure out what the value of x0 is using these samples. Okay, and this is a question that has been studied a long time ago, and it's a very practical question which is used all the time in quantum metrology, and or just even in classical statistical inference. And it turns out that this variance quantity has a lower bound over all possible choices of the estimator function. And this lower bound can be expressed just in terms of some intrinsic properties of the probability distribution, which don't depend on the specific choice of this estimator function. And this is given, this lower bound is given by 1 over n, where n is the number of samples, times something called the Fisher information, which is this object. Okay, so it involves a sum over all possible measurement outcomes of this combination of the derivative of px with respect to x and the actual probability. And this inequality can also be saturated by some particular choice of this estimator function. So this classical Fisher information actually gives a pretty good sense of how well you can estimate the parameter by using samples. Okay. Any questions at this point?
So did you say that this was independent on the estimator? Like the probability distribution is just a function of...
Yeah, this quantity at the lower bound is independent of the estimator. And it's realized for some particular choice. So this is true for any estimator, but you can even give an explicit thing which saturates it, which tells you that it's actually a good measure of how well it can be estimated. Great. Any other questions? Okay. So for any choice of the measurement basis, we found that our ability to estimate any parameter x is quantified by the classical Fisher information, which is this object. But now, if we have a quantum state, then we can also choose what basis we want to measure in. And we can try to maximize the value of this quantity over all possible choices of the quantum measurement. Okay, and this was done by Bronstein and Cades also many years ago. And it can be found very explicitly, and the resulting quantity is called the quantum Fisher information. Okay, so there is an explicit formula for it, which I've written down here. Mostly, I just want you to notice that this is a formula which depends on derivatives of the density matrix with respect to x. And it depends on both the eigenvalues and the eigenstates of the density matrix. Okay, but it's something very explicit, which can be written down and calculated. But one thing is that this optimal measurement basis actually depends on the state rho of x. So in particular, this means that now this tells us if we already have some idea of what x is, then we can choose to measure in this basis, and we can locally improve our estimate and figure out, like, if the actual value is x plus delta x, then what is delta x? Okay. Yeah, and then another sort of more useful way of writing this quantity is in terms of some distance measure between the state at x and x plus dx, and some kind of derivative of the state. Okay, so the Beer's distance is just one of many choices of distance measure, and the quantum Fisher information happens to be related to it. And so this tells us that somehow this quantity can be viewed as some kind of intrinsic velocity at which the state is changing with respect to the parameter x. Okay. Okay, so now we want to apply this in the particular case of time evolution. So we imagine that we have some quantum many-body state, psi 0. It's evolved to time t plus delta t by h, which is some quantum many-body Hamiltonian. And say we know what things like psi 0 and h are, and we know that the time is close to t, but we want to make measurements on the state that's given to us in order to deduce what delta t is. Okay, so the quantum Fisher information of the whole state psi of t will tell us how good our estimate for delta t can be using optimal measurements on the whole system. Okay, and then another thing we can consider is the reduced density matrix rho a of t for some subsystem of the whole system. And then we can look at the quantum Fisher information associated with that, which tells us the optimal thing that we can do on some subsystem. Okay, so this is the main setup. So any questions at this point? Okay, so okay, so now, as I mentioned at the beginning, from this intuition that our state is relaxing to a steady state, the most natural thing to expect is that this quantum Fisher information will monotonically decrease and then eventually go to 0 as you reach some steady state. Okay, at least this is what I originally thought would happen. And you can, this question has actually been studied somewhat recently in the context of just classical stochastic evolutions, where you can consider some classical probability distribution that's evolving under the Fokker-Planck equation, which leads to diffusive behavior and some kind of relaxation dynamics. And in that case, you find that the classical Fisher information does have exactly this behavior where it monotonically decays and then goes to 0. Okay. But in contrast, if you look at the quantum Fisher information of this time-evolved state for the whole system, okay, then you find that it's always just a constant with time. Okay, so it doesn't decay at all. And in particular, if you consider the case of a pure state, then it's just equal to the variance at time t, which is, as we know, equal to the variance at time 0 of the energy. And so in particular, if you have an energy eigenstate, then this quantity is 0, which makes perfect sense because the energy eigenstate is not evolving at all, so you can't use it to estimate time. But if you consider a local Hamiltonian and some state like a typical product state on the system, then this variance is proportional to the volume of the system. So the value of this Fisher information is quite large. And this tells us that you can do, in the thermodynamic limit, you can do a pretty good job of estimating what the time is using the whole system. Okay. Yeah, so this what we've learned is that if we're allowed optimal measurements on the whole system, our ability to distinguish the state at rho t at time t from t plus dt is independent of t. And this is similar in spirit to the statement that the von Neumann entropy of the whole system under some unitary evolution is a constant. Okay, so it's again capturing the fact that on the whole system, somehow information is not lost, it's just scrambled in some. Okay, so now in order to see something that might align more with our intuitions about thermalization, we can again consider the reduced density matrix of some subsystem. And then the corresponding quantum Fisher information has this form, where again, I just want you to notice that now, essentially because you're doing this partial trace, the earlier statement that it becomes independent of time is no longer true. And now it's some complicated expression, which it's hard to evaluate directly in any given system. And one feature of this expression is that it depends on both the eigenvalues and eigenstates of the reduced density matrix, rho a of t. And in fact, it also depends on properties of the global state. So it doesn't even just depend on the reduced density matrix. And so, unlike the entanglement entropy, which has the property that it's equal for a subsystem and its complement, this is no longer true for this Fisher information. Okay. So the plan for the rest of the talk will be to first discuss some numerical observations of how this quantity behaves in chaotic spin chain models, which will also give us a prediction for how it should behave in the black hole and radiation setup that I mentioned. And then we'll try to physically understand where these results are coming from by using very simple models and arguments. And then I'll make the connection to the Hadron-Prescott protocol and information recovery a bit more precise. And finally, I'll consider a different kind of Fisher information, which is the classical Fisher information associated with simple measurements on the system. Okay. Okay. So let me summarize the numerical results. So we're considering some chaotic spin chain model like this, which has been studied a lot in the literature on quantum chaos. It turns out to predict universal properties of chaotic systems pretty well by many different measures. And in particular, if we consider initial random product states in this kind of system, then if we look at the evolution of subsystem entanglement entropy, it has a very simple behavior where it just grows linearly and then saturates. And this is very similar, for instance, to the behavior in holographic CFTs. Okay, and the eventual saturation value depends on the size of the subsystem that we're looking at and is just given by the page value. Okay. So in the current setup, we'll consider the Fisher information of some subsystem A of size NA on a whole chain of size N. Okay. Okay, so the first thing we can look at is to fix the size of A and then increase the size of the whole system. Okay, so we fixed NA to 1 and we're changing N from 8 to 12. And we find firstly that with time, this quantity just monotonically decreases. And then it reaches some saturation value. So I'm plotting the log here. And the saturation value is roughly equally spaced for different sizes of N. So it's exponentially decaying with the size of the whole system for a fixed subsystem size. Okay, so if you consider the case where you have a very small system compared to the whole system, then this aligns pretty much with what we expected from thermalization, that at late times, the state is evolving very little. Okay. And we can do a more careful analysis where we vary the size of the subsystem for various sizes less than half of the whole system. And we find that the scaling is like dA squared over d, where dA is the subsystem dimension and d is the whole system dimension. Okay. Yeah.
Initially, it's so large because it's a Hamiltonian distance. Or like it's an anybody, like so
Yeah.
the initial state has a lot of uncertainty
Yeah, exactly.
in the energy.
Right. So the initial state has a large energy variance because it's a random product state, and you have some local Hamiltonian. And as I mentioned, such states have variance proportional to the volume.
And that's also, that means like the sensing is going as 1 over n. The Kramer bound is 1 over n as opposed to.
Yeah, it's 1 over n. Yeah, sorry, n was the sample number, and right. But now it's small n is the size of the system, and it's going like 1 over small n.
The something you're able to sense something like 1 over v as opposed to 1 over square root v. Like the normal, just like if you had a bunch of different samples, the ability to.
Mm-hmm. So yeah, in that case, is it the uncertainty that goes like square root v, or is it okay? Yeah.
When it's intense, it's 1 over v.
Mm-hmm.
This is intense.
Yeah. Great. Any other questions? Okay. So right, but then the eventual saturation value is quite small and it's exponentially suppressed in the dimension of the whole system. Okay, but now if we consider a subsystem bigger than half of the system, then we see a sort of dramatic difference. So in this plot, we're fixing the size of the whole system. We're fixing the size of the whole system to be 10 sites and then increasing the size of the subsystem from 1 through 7. So we see that up to the halfway point, we're just seeing what we were seeing before, which is that the value is pretty small and there's monotonic decay. But then for subsystems which are bigger than half of the system, we see that there is actually a non-monotonic behavior with time. So there is actually an increase at intermediate times. which is quite counterintuitive from the perspective of thermalization. And then the eventual saturation value is suddenly quite large. So beyond this point, the saturation value becomes approximately proportional to the volume of the subsystem. Okay. So this was for the chaotic case. We can also consider an integrable case of the same spin chain model, where we turn off the longitudinal field, and this just becomes a transverse field Ising model, which is a free fermion system. And in this case, we find a very different behavior of this quantity. So let's first look at, again, the case where you fix the subsystem size and increase the whole system size. In this case, the saturation value no longer is decaying with the size of the whole system. Okay, so it's just a constant with respect to the whole system size. It only depends on the subsystem size. And it you can see that these are much larger values than we were seeing before. And roughly the saturation value is proportional to the volume of the subsystem for any subsystem size. Okay, so this is telling us that in this integrable case, the state is reaching a steady state to a much lesser extent than the chaotic case. Another sort of surprising thing is that in this case, there is a non-monotonic evolution with time, even for the case of a smaller subsystem. Okay. One thing to note is that if we had instead considered the behavior of the more standard observable like entanglement entropy in this setup, then it's almost the same, at least the saturation value is almost the same between the integrable and chaotic cases. So in both cases, it reaches roughly the page value. So this quantity is able to detect the difference much more sharply in the saturation value.
It's a closed chain.
Yeah.
This feature, does it have something to do with sort of surrounding the whole chain? Like wrapping around, like what is the time scale at which this dip happens?
So the time scale at which the dip happens, like at which it turns around, seems to be increasing a bit with the size of the whole system, like in this part.
It's like the wrapping time.
I'm not exactly sure. Like, I don't know exactly how to make that precise because that size is proportional to the subsystem size. But like, do you have in mind some other measure of things wrapping around?
Curious.
Yeah, I don't fully understand this non-monotonic time evolution very well, but I think. Yeah, I don't immediately have comments on that. Any other questions? Okay. Right. So let me try to discuss some physical interpretation of the numerical observations, in particular, starting with this late time saturation value in the chaotic case. So for any quantum state, pure state psi, there is some Schmidt decomposition between a subsystem and its complement, where these are the Schmidt eigenvalues, and then you have the eigenstates in A and A bar. So this is a completely general fact. And we can give an explicit expression for the subsystem Fisher information in terms of the Hamiltonian and these PIs and the Schmidt eigenvectors in both A and A bar. We can now try to use this expression in a simple model to try to understand the late time value. Okay. So a frequently used model, which I had mentioned at the beginning in the discussion of the page curve, is that the whole state, combined state on A and A bar is like a Haar-random state in the full Hilbert space. And in principle, this would be a nice model to use, but as you might have noticed from the expressions that I wrote down, the quantity that we're discussing is quite complicated, and actually finding its value in a Haar-random state would require a very complicated replica trick calculation. Okay, so it would be nice if we can find some even simpler model, which lets us avoid that. And so we used this even simpler model, which is somewhat similar to a Haar-random state, where if A is the smaller subsystem, then we assume that all the Schmidt eigenvalues are roughly equal to 1 over square root of dA, where dA is the dimension of A. And then we can choose any basis for the Schmidt eigenvectors in A. And for the states in A bar, which these are entangled with, we can choose any fixed set of orthonormal vectors in A bar of size dA, which is smaller than the whole size of dA bar, but then completely scramble them by using some random unitary. Okay, so this is like some, the whole system A entangled with some random basis in A bar, which is of the same size as DA. Okay. So this is not an entirely accurate model for a random state, because actually there is some non-trivial distribution of these eigenvalues, and there is some level repulsion between them, and so on. But it will turn out that it's actually a pretty good approximation. And even if we try to include some of these effects from level repulsion by taking the actual probability distribution of eigenvalues of a random state, the answer will remain the same up to exponentially suppressed things. Okay. But now the nice thing about using this model is that we can do the calculation of the quantum Fisher information in both A and A bar very directly in this kind of state. And I can provide more details on this calculation at the end if people are interested. And note that in this model, I didn't put in anything about the fact that the state had actually been obtained from evolution by e to the minus IHT. Okay, so I've forgotten all of that and just I'm choosing a completely random model. But despite that, it'll turn out that this model will reproduce the scaling of the late time value very well. Okay. Okay, so from doing the calculation that I described in this kind of model, where the whole Hamiltonian is assumed to be local, so it has a structure of some terms in A plus some terms in A bar plus some interaction term in between. Then from that calculation, I find some expressions for the Fisher information, which depend on the dimensions of the subsystems and various combinations of the terms in the Hamiltonian. But the overall result is that if NA is smaller than N over 2, then we find dA squared over D times the area of the boundary of the region A. And if NA is bigger than N over 2, then we just find this volume law scaling. Okay. And so this matches the qualitative behavior I mentioned before. We can also do a more direct comparison. So in this plot, these circles are the actual late time values obtained from the spin chain model after averaging over late times for different sizes of NA and the whole system size N. Okay. And then if you consider the same system sizes and consider the value obtained from this toy model, which means this expression and also some subleading corrections for smaller subsystem sizes, then you get the value in these stars, which the qualitative behavior is similar, and of course the numerical values don't match exactly. But now we can also take the n going to infinity limit in this toy model, where we see this sharp transition that I described here, from a value that's negligible up to the halfway point, and then suddenly increases at the halfway point, and then continues to improve beyond that time. Okay. And then even from these spin chain results for n from 8 to 12, we can see some evidence that the transition is getting sharper as you go from 8 to 12. Okay. Okay. Great. Any questions?
So late times, I assume you're not recurrence times like a wave.
No. By late times, I mean just like I'm averaging over sometimes in this regime, these plots.
That's like, yeah, way before.
Yeah. So I just mean that sometimes after which this has saturated. Okay. Any other questions? Okay. So in particular, in the case of the black hole, if we take A to be the radiation, and so which is the most natural choice, because in principle we're allowed to make measurements on the radiation, then we see the sharp transition that I was mentioning at the beginning, where before the page time, our ability to estimate time is very poor, and then suddenly it improves at the page time, and then continues to improve up to that point. Okay. Okay, so let's try to see whether we should have sort of intuitively expected this kind of result. So one thing that is very well established in this literature on thermalization is that if we consider the time evolved late times reduced density matrix rho A of t, and we have some subsystem which is less than half of the system, and we average the distance of this state from the maximally mixed state over all times, then if we have some appropriate ensemble like this random product state ensemble that I'm considering here, which equilibrates to the maximally mixed state, then this distance is suppressed with a similar kind of scaling. So it's suppressed like dA squared over D. Okay, but this is the average over all times under various assumptions. And then in this more recent paper, it was argued that even if you consider fluctuations from this average over all times at any given time, then this quantity is also pretty small. Okay, so not only is the average over all times consistent with this bound, but also at any given time, it's very unlikely that you'll be very far from the maximally mixed state. Okay, so if the whole state is equilibrating to something, then it seems to make sense that it's the rate at which it's changing will also slow down. So the thing that we've considered here is I mentioned this expression for the Fisher information, which is this Buras distance between the state at time t and time t plus dt. So it's some kind of it's different from both of these things because it's more like the speed of fluctuations, which in principle could have been larger than either of these quantities. But it turns out that in practice, it's not, and the fluctuations are not only very small, but also very slow. Okay, and they're suppressed in the same kind of way with this dA squared over d scaling. Okay, but yeah, roughly what we found is consistent with our usual expectation that the state on the smaller subsystem is equilibrating to something which is the maximally mixed state. But now if we consider the larger subsystem, then it's still true that its eigenvalues are equilibrating and roughly approaching this flat spectrum of 1 over dA. But now, so at late times, the state looks something like 1 over dA times the projector onto some set of eigenstates in A bar. And this is a D, so even if A bar is a bigger system, this subspace is still dA dimensional, just from the fact that our state was a pure state. Okay, and essentially what we're learning is sort of a precise sense in which this projector onto the eigenbasis is not equilibrating to anything. So we have a small subspace of dimension dA in this whole system of dimension dA bar, which is much larger. And this eigenspace is just kind of freely rotating around for arbitrary times in this larger subspace. Okay. And this is quantified by this extensive value of the Fisher information at late times. Okay. And we can also try to understand, so what I discussed so far was just the equilibrium value and the fact that it's small in one case and large in the other case. We can also come up with some model for the time evolution, which is simple enough that we can actually do concrete calculations. So if we assume that we're interested in the part of the equilibration process where the eigenvalues have all equilibrated to a value of 1 over dA, but then the eigenstates are still rotating. So we choose some simple basis of phi I in A bar, and then act on it with some unitary matrix, which now is not completely Haar-random, but it's something which is approaching a Haar-random matrix at late times. Okay, so the simplest thing we can do is consider a time-dependent random Hamiltonian evolution for this UA bar. And that we can do very precise calculations. And then in this model, we find that for a smaller subsystem, this Fisher information is monotonically decreasing. And for a larger subsystem, it's monotonically increasing. Okay, so in particular, this gives us some sense of where this increase at intermediate times in the Fisher information that I showed in the spin chain system is coming from. And roughly, this is happening because at later times, my eigenbasis of the reduced density matrix in A bar is getting access to more and more of this large Hilbert space to sort of swim around in and explore. Okay. Yeah.
You have to make some assumption about how these basis states are related to the Hamiltonian.
No, in all of these models, I'm not even making any assumptions about that. Like to get in, but okay, so I find that this monotonically decreases and monotonically increases, and it essentially, this model is very crude, so I don't find anything like a good approximation of the actual time evolution. I just am able to replicate the increasing or decreasing behavior. So to actually see the way in which it's increasing or decreasing, I would probably need to take into account some constraints from the actual Hamiltonian.
Is the Hamiltonian fully not knowable? Is that like why this all works?
No, I'm using a so these results that I mentioned were for a chaotic spin chain Hamiltonian. But this last result that I mentioned, I'm assuming that this UA bar of T, which is scrambling the Schmidt eigenvectors, is like a non-local random GeV Hamiltonian. So that is not going to, yeah, so right. So the timescales that I'll get for that will not be consistent with what I get for the spin chain system. But just the fact that it's increasing or decreasing with time, that part can be captured even with this completely non-local model. So yeah. So when I say that like the eigenbasis of rho A bar has access to more and more of the Hilbert space at later times, that doesn't have to come from a constraint due to locality. It can also just be a constraint in a non-local Hamiltonian. Initially, you have access to less of the Hilbert space, and then eventually you have access to more of the Hilbert space. But in the non-local case, probably all this saturation will happen at some order 1 time. Right. In this case, things are scaling with the size of the subsystems. Okay. Any other questions?
Maybe this is a red herring, but at least qualitatively, the nature of your Fisher information with time, qualitatively, the graph is very similar to the spectral form. Is that a coincidence, or is there?
Yeah, you mean for the larger subsystem where it goes down and then increases? So far it seems like a coincidence. Yeah, let me say that so far it seems like, so the spectral form factor is known to be related to, in some sense, to something called the Krylov complexity. And I think that there might also be a sense in which this quantity can be related to the Krylov complexity of the time evolving density matrix. But I think that needs to be formulated more precisely. So, yeah, but it might be related. Okay. Okay, so now the fact that this Fisher information, like the expression for it, involves the Schmidt eigenvectors, also explains why it's so different between the chaotic and integrable cases. So in the integrable spin chain, we can essentially give a pretty good qualitative description of what is happening with a model where you just have free streaming quasi-particles. So you imagine that like at some initial time, some quasi-particle pairs were created, which were maximally entangled with each other and close to each other. And then under the dynamics, these quasi-particle pairs, which are entangled with each other, sort of go away from each other in straight lines like this. Okay, and then this sort of explains a picture for how entanglement spreads out in this model. So at any later time, if I consider some small subsystem, everything in it is entangled with the region outside. So again, it's true that the entropy will grow to the page value and become proportional to the volume of the subregion. But it's entangled with the outside in a very different way, where now the Schmidt basis, instead of being this completely random basis that I described, is now just some product basis. Okay. And unlike the entanglement entropy, the present quantity is able to detect this difference in the Schmidt basis. And using this quasi-particle model, we can reproduce this proportional to NA behavior of the subsystem Fisher information. And as Thomas suggested, there might be also some picture for this non-monotonic time evolution in terms of the quasi-particle model, which we haven't looked into yet. Okay. Okay. So now let me discuss the comparison of the story that we have here to the Hayden-Prescott protocol. Okay, so like in the Hayden-Prescott protocol, we found that there's a sudden ability in our sudden improvement in our ability to do something after the page time. And in this case, the something is to estimate time. Okay, and let me recall sort of more formally what happens in the Hayden-Prescott protocol. So in that setup, we imagine sort of a quantum error correction setting where we isometrically encode 1 qubit into n qubits in this way, where we have some fixed state size 0, and then we combine it, we take a tensor product of it with either 0 or 1, okay, or whatever state we have in the diary, and then act with some random unitary or some like highly chaotic time evolution. Okay, and then at later times, we divide the output into 2 parts, B and R, and we consider a channel from the state on D to an output state on R where we trace out B. Okay, and then the question that we ask is, about whether the original state is recoverable from this channel, which is equivalent to the question of whether any two states, psi d and phi d of this input system, remain just as distinguishable after this channel as they were before the channel. Okay, so and the conclusion from Hayden and Preskel is that any two such states can be distinguished can be perfectly distinguished if dr is bigger than dB, but cannot be distinguished at all if dr is less than dB. Okay, so in particular, we can phrase this in terms of a quantity called the fidelity, or various other distance measures. But in terms of the fidelity, we say that the fidelity between the output states is 1 if dr is less than dB. And fidelity being 1 means that you can't distinguish the states at all. And if dr is bigger than dB, then the fidelity is immediately what it would be in the input. So you can distinguish them just as well as you could on the original system. Okay, so I'm going to try to phrase the task that we have here, this time estimation task, in a similar language to this. Okay, and the task that we have is essentially to distinguish the state psi of t from like the Taylor expansion of psi of t plus dt. Okay, which basically just differs from the original state by a path where h is acting on psi of t. Okay, so in this case, we can consider an isometric encoding of 1 qubit into n qubits, which is different from the previous one. So we send 0 to the state where we evolve some fixed state psi 0 with the chaotic time evolution u. Okay, and we send 1, in 1, we don't change something in the input, but in the output state, we then act with h. Okay, and then roughly, in order to have a proper isometry, we need to also orthogonalize this with respect to the 0 state. Okay, and so now in this case, like our task of estimating time is somewhat similar to this task of trying to distinguish the state 0 from the state 1 after tracing out some subsystem B from the output. Okay. And now we can again consider the fidelity. So we can consider the 0 and 1 states before we trace out and act with the channel. 0 and 1 are perfectly distinguishable, so their fidelity is 0. And we can now ask what the fidelity becomes after acting with this channel. And we find that the fidelity is again 1 if dr is less than dB. So those two states which were perfectly distinguishable have become perfectly indistinguishable if the dimension of the radiation is smaller than that of the black hole. But then if you consider dr bigger than dB, so after the page time, there is a sudden improvement because this 1 now becomes 1/2 in this case. And then it continues to improve until the page time. And so the distinguishability becomes perfect only at the end of the evaporation process in the setup. But there is a sudden improvement at the page time. Okay, so this can be an alternative way of understanding like why our results were similar to, but also different from the Hayden-Preskel protocol. And somehow what is happening here is that unlike in the Hayden-Preskel protocol, where we're using the full power of this random unitary to scramble and encode information, in this case, we're not really using the whole thing because we're just sending the two states to the same state and then changing them a little bit by h. Okay, but still having a random unitary here does help in the sense that there is a dramatic improvement after the page time. Okay. Okay, so in the last few minutes, let me switch gears a little bit. So far, we've considered the quantum Fisher information, which is, as I mentioned, the classical Fisher information associated with the optimal measurement basis. And one conclusion that we've come to so far is that in this black hole evaporation setup, the quantum Fisher information has a very different behavior in the reduced density matrix of the state after the page time, and in the actual thermal density matrix. Okay, because in the thermal density matrix, its value is just 0, but in the actual time evolved chaotic state, its value is extensive in the volume of the radiation. Okay. And of course, a more familiar quantity which distinguishes rho r after the page time from the thermal density matrix is just the entanglement entropy, which according to, in the thermal density matrix would just keep being proportional to the volume of the subsystem, but in the actual time evolved state becomes proportional to the volume of the complement. But Engelhardt and Wall tried to defines some kind of coarse graining procedure, which would lead to an answer which actually agreed with the thermal density matrix. Okay, so they wanted to find out sort of what you can do to the reduced density matrix of the radiation in order to still see Hawking's information loss. And they considered this coarse graining procedure involving the so-called simple entropy, where they considered the actual state rho, and then they considered all possible other states sigma, for which the expectation value of all possible simple operators by some notion of simple agreed between these two states. Okay, and the simple is like phrased in terms of computational complexity. An example of a simple operator is just say all the possible Pauli Z strings or something. Okay, so basically, if we consider all possible states sigma, for which up to exponentially small corrections, the expectation values match between rho and sigma, then we can maximize the entropy over all possible choices of sigma. Yeah, one can make the argument that if we consider the reduced density matrix of the radiation after the page time, then the associated simple state will just be the actual thermal density matrix. And so the simple entropy will be extensive in the volume of the subsystem and will reproduce Hawking's information loss. Okay. So in this context, a natural thing to ask is, what if you considered this Fisher information not the one associated with the optimal measurements, but just the one associated with some simple measurements on the system? Okay. Does this now again behave exactly like in the thermal density matrix, or does it still distinguish rho r from the thermal state? And intuitively, based on these discussions of simple entropy, my expectation was that the classical Fisher information associated with simple measurements would just decay to some exponentially small value late times. Okay. But if we actually look at its evolution again in this spin chain model that I described, then for different system sizes, so we can first just look at the full system. Okay, and we are considering the evolution of the classical Fisher information and just the computational basis of like Pauli zeros and ones. Okay, and this is the numerical result that it decays, but just by some order 1 amount. And then the eventual saturation value is still extensive in the subsystem size. Okay. So in particular, this is very different from the value that we would see in the thermal state, which would just be 0 because the thermal state doesn't evolve at all. Okay, and then we can also look at the classical Fisher information associated with simple measurements on some subsystem. And again, we find that this quantity has a volume law behavior for a subsystem that's bigger than half of the system. So in particular for the radiation state after the page time. Okay. And then we can also reproduce this volume law behavior by considering how random states. Although the actual coefficient of the volume law is different. So yeah, so the value in the random states is shown with the dashed lines, which again are proportional to the volume, but differ in the precise value from the value in the spin chain late time state. Okay, so basically what we're finding from this is that the classical Fisher information associated with simple measurements does still sharply distinguish the reduced density matrix of radiation after the page time from the thermal state. Okay. So my intuition that this would not happen was based on the fact that just as the reduced density matrix of the time evolved state on some subsystem equilibrates to something, which is the maximally mixed state, it seems naively that the probability distribution associated with simple measurements in a random state it also just approaches the uniform distribution. Okay. And this is true if you look at the difference in probability of getting a particular outcome psi between the random state and the uniform distribution. This quantity is exponentially small in the system size n. But actually, if you consider a measure of distance between the two probability distributions, that involves summing over 2 to the n things. And there is some competition between these two, as a result of which any measure of distance between the two probability distributions is actually order 1. Okay. So the trace distance is order 1 and the relative entropy is also order 1. And this finite distance of the late time of the probability distribution, the random state, or the late time probability distribution from the uniform distribution makes it less surprising that the classical Fisher information is still large at late times, because this distribution is not really equilibrating to anything. Okay. Yeah, and the actual value of the classical Fisher information in this case, which is like some kind of derivative of the relative entropy between the distribution at time t and distribution at time t plus dt, is proportional to the size of the system. So it has some extensive scaling. Okay. Okay, so let me summarize what we did in this talk. So there are two important differences between the thermal density matrix and the time evolved state at late times. One, which is discussed often in the context of the black hole information problem, is that the thermal density matrix contains very little information, but psi of t at late times contains information in a very scrambled form. And then another important difference is that the thermal density matrix does not evolve with time, whereas the psi of t necessarily evolves with time. And what we did in this talk was to consider a new task of time estimation, which sharpened our understanding of the second point. We found that the task can be performed very poorly on less than half of the system, but much better for more than half of the system. And we understood this from a toy model of the state, similar to a hard-random state. And one interesting fact that we found is that this quantum Fisher information is sensitive to the structure of the Schmidt basis in which the state is entangled, which leads to a very sharp distinction in its value between integrable and chaotic systems. And yeah, we found somewhat surprisingly to me that the classical Fisher information associated with simple measurements is still extensive in the system size at late times. Okay. And then a natural question to ask is, like, so right now I don't know how to calculate this particular quantum Fisher information associated with time in semi-classical gravity, but if we could, then would we see some form of information loss similar to what we see in the case of the entanglement entropy? So this, just based on our usual expectations about information loss, we would expect maybe that the Fisher information after the page time would still appear to be very small as opposed to extensive. Yeah, and then, well, first one needs to see whether one does indeed get some analog of the information paradox, and you could ask about whether it would be resolved in a similar way to recent discussions of the reproducing the page curve by introducing new elements in semi-classical gravity, like elements in replica moments. Yeah, so that's it. Thank you.
This comparison between the temperature state and the completely hard-random state have to do with like these quantum supremacy experiments, and they're like, yeah, in there, and eventually they lose supremacy if they have too many errors.
Okay, yeah, I don't know that literature very well, but yeah, so like this has probably been discussed somewhere in the literature before, but I haven't seen an explicit discussion of it. The fact that there is even a finite trace distance between these two distributions. Are you referring to some other application of this fact?
Yeah, no, I was thinking actually about the slide that I agreed that first I would think there's no possible Fisher information. But then I was thinking about these quantum supremacy experiments, and they're seeing some very sharp structure in the distribution of simple observables.
Okay. In what context?
So they take some product state, they have a sequence of unitary gates like virtual circuits, and they make measurements in the feed. So they're trying to get some hard-random state. They make Z measurements, and then they're looking at like the distribution that they're getting, and they're trying to say that there's some really crazy structure that couldn't be produced by some random measurements.
Oh.
I guess that's kind of, in a sense, you also said there's some exotic structure that can detect the changes in time. I don't know, that it's just.
So in their case, they're comparing the state that you get from some circuit evolution for some finite time to a completely hard-random state and seeing a difference?
Yeah, I think they're trying to get times similar to the studies.
Okay. But in this case, actually, the qualitative behavior is also the same for a hard-random state. Okay, so the exact value is different, but the fact that it's extensive, so yeah, the dashed lines in this figure are supposed to show the value of this quantity that you see in a hard-random state. And that is also actually pretty large. So there isn't like a very, right, but then you could ask where this difference between these two things is coming from. And this is probably a consequence of some local structure in the Hamiltonian, which is somehow imprinted on the late time state. So yeah, this gap between these two values might be related to what you're saying.
How do you estimate the classical fish?
Like how do you do the actual calculation? So the plot that I'm showing here is for just numerically sampling over high random states. But if you do, you can do a simpler thing where you can ignore the normalization constraint in the state and then just treat the individual. So say that I have some simple basis psi.
Are you actually evaluating the derivative of the probabilities for all exponential?
Yeah, right. And everything can be written in terms of like, say that n is labeling my simple basis, which goes from 1 to 2 to the n. Okay, so you can treat each of these as some Gaussian random variables. And if you assume that the dimension of the system is large enough, then you can essentially ignore the normalization constraint and assume that they're all independent Gaussian random variables, which are drawn from some distribution like this. Okay. And then, then there's an explicit expression for the classical Fisher information associated with this probability distribution. And with this Gaussian constraint, it can be simplified and you get an answer which again has the right volume law scaling. The funny thing is that it involves, that expression involves some things in the denominator, like essentially because the expression for the classical Fisher information looks something like this, right? And so this is like, in our case, it's like Cn squared. So you get some funny things with like some factors in the denominator, but then you can deal with them by the fact that under Gaussian averages, everything factorizes. So you can separately average this part in as well.
Since you don't have to use, like, this is rather generic distributions, they're not like some weird fine-tuned thing.
No, yeah, exactly. Just to reproduce the volume law scaling, you don't need anything very fine-tuned. What we're not able to reproduce is this sort of difference in the volume law coefficient.
So what we have a measurement set up, like if I want to know whether the black hole actually evaporates unitarily or like in the thermal, like thermal state, like whether there's information loss or not, what should I measure as infinity?
Yeah, like if I wanted to measure this Fisher information, how would I measure it? Yeah, that's a good question. So it's, in principle, I need an infinite number of copies of my system in order to, yeah, so basically this measures like I'm using n copies of my system in order to make a time estimate, and this is quantifying the variance in that time estimate. So I need some large number of copies, and then I want to see how the variance is decaying with the system size. So it's certainly not something that can be done using just one copy of the system.
Let's say you have, like, you can theoretically form n copies of black hole formation and subsequent evaporation. Then you, in these n copies of your thing, of your setup, you would measure the radiation. Always, like you have that more tight thought experiment detector. And then from that, you would be able to say, like, about this time evolution, how does Fisher information evolves.
Yeah, then you perform this measurement. Say you just do this measurement in the computational basis, you put it into your so you can, I mentioned that there was some explicit form of this estimator function. You can use something called maximum likelihood estimation, and you can like get some estimate for your values of time, and then you can like repeat this experiment multiple times and see how much the different time estimates you're getting are varying from each other. That gives you a measure of the variance.
Is there any hope of forming such a computation for, like, let's say, short shelf, starting from short shelf black holes in GR?
I think what you might be able to calculate is just in a similar way to how we know how to calculate things like entanglement entropies. You might be able to calculate these expressions. like these kinds of explicit expressions for the Fisher information. Like it involves a different combination of partial traces from the entanglement entropy, but like, yeah, I don't know what the best way to do it would be. Like one way might be to introduce, there is a way to write this expression involving some number of replicas of the system and doing some replica trick. It would be much more complicated than the usual replica trick that we do for entanglement entropy. But in principle, that would then translate to some kind of gravitational path integral, and you can compute things in it. But I don't have a very concrete idea of how to do that calculation.
Like performing the maximum likelihood estimation, you need a full model. Is it the case that you need a full model of the probability?
Yeah, right. So in this case, this is why I said at some point that we're assuming that we know what size 0 is and what h is. So then we do have a model for the probability distribution. The only thing we don't know is the precise value of time. Yeah, but this is something that I actually want to try on the spin chain, just like do an actual simulation of drawing samples and seeing what the maximum likelihood estimation predicts, and see how that compares to the actual value of time.
Okay, let's play the again.